Hey guys, and welcome to the very first video on radioactivity and particles, which is the new topic we're going to be discussing today. And of course, first off, we'd have to take into account the concepts behind radioactivity and particles. Whereas in the previous topic, we were looking at electricity, and it got into a lot of practical uses. Radioactivity and particles is very, very minuscule and tackles mainly the atomic nucleus. And of course the atomic nucleus is incredibly small, and radioactivity is just basically talking about the emission of subatomic particles or electromagnetic waves from the nucleus as a means of staying stable. First off, let's just take a look at the physical definition of radiation, which is basically the emission of electromagnetic waves or subatomic particles. And it should be from an atomic nucleus or an atom. That's basically what radiation is. Now, before I talk about exactly why atoms emit radiation, we'll have to talk about a few different concepts first. The first one is isotopes. Now, this might seem like an unfamiliar word to some of you, but what exactly is an isotope? Well, isotopes of a certain element are just basically different nuclear formulas for the same element. And we all know from chemistry, or at least most of us know, that different elements, for each element, has to have the same number of protons. So what I mean by isotopes is that it has the same amount of protons but a different amount of neutrons. And this means that it's still exactly the same element, but it constitutes to a different atomic mass, although the proton number, the atomic number, stays exactly the same. So for example, we've got helium-4, which is an isotope of helium, one that we're very familiar with 2 protons and 2 neutrons. The atomic mass is 4, and it's got 2 electrons orbiting the nucleus. Now we've got helium-5. If you look carefully, you'll see an additional neutron inside the nucleus. It still has 2 protons, so it's still helium, and it still has 2 orbiting electrons, so its chemical properties are generally exactly the same. So those are isotopes, just different neutron numbers for the same element, which has the same protons, or the same amounts of protons. Alright, so now let's take a look at the forces at work inside the nucleus. We learned from electricity that opposite charges attract and like charges repel. And we all know, or at least some of us know, that protons are all positively charged and neutrons have no charge, which I'll discuss in further detail in the next video. So if we take into account all of the protons inside the atomic nucleus, the question is, how does the nucleus stay intact without all the protons spontaneously repelling each other? Well, first we have to take a look at what we call the strong nuclear force, represented by all the purple arrows inside the nucleus. The strong nuclear force I'll explain in more detail in the particle physics chapter, but generally, if we look at the nucleus, this strong nuclear force is a force which binds all nucleons together with other nucleons that are directly next to it. So basically, the strong nuclear force attracts protons with protons, attracts neutrons with neutrons, and attracts protons with neutrons. It binds these nucleons together. Take into account that the strong nuclear force has a range of about the radius of 1 nucleon. That means that inside the nucleus, each nucleon will only attract other nucleons that are directly next to it. Now the next force we can take a look at is the electromagnetic force. And here we call it the Coulomb force, which attempts to repel like charges from each other. The confusing yellow arrows are supposed to show that each proton repels each other proton. So, since the electromagnetic force is infinite range, the protons don't just repel other protons which are right next to it, like the strong nuclear does with attraction. Instead, the electromagnetic force affects every single proton. So every proton repels every other proton. And this means that the electromagnetic force seemingly has a lot more dominance over the strong nuclear force. But the reason the strong nuclear force is called that is because it's so strong, much stronger than the electromagnetic force. If we look at the big yellow and purple arrows, we can see that the electromagnetic force is attempting to rip apart the nucleus, whereas the strong nuclear force is attempting to bind the nucleus together. But then the question is, what happens when the nuclei get too large? We've got atoms and elements such as uranium with incredibly large nuclei. Now think about that. In uranium, every single nucleon is of course attracted to every other nucleon right next to it by the strong nuclear force, but it's also repelled to every other proton in the entire nucleus by the electromagnetic force. That means the bigger the nucleus, the more dominant the electromagnetic force is going to be, simply because as the nucleus gets bigger, the electromagnetic force gets stronger, whereas the strong nuclear force doesn't really have that much of a change. So that is why some nuclei are unstable, simply because the amounts of protons and neutrons they have mean that the electromagnetic force starts to overpower the strong nuclear force. And that's why some atoms and nuclei are in trouble. They tend to nearly break apart. And that is why they emit radiation. By emitting radiation, the nucleus is able to decrease its mass and turn itself into a lighter element. This turning of itself into a lighter element means that the nucleus is no longer at risk and the electromagnetic force is no longer overpowering the strong nuclear force. So radiation, this giving out of particles, is simply an attempt by the nucleus to save itself from immediate destruction by the electromagnetic force. Now, when I mentioned that the amount of protons and neutrons affects the instability of a nucleus, if the nucleus just happens to have too many neutrons for its proton number, or too little neutrons for its proton number, and that generally makes it slightly unstable. This next slide shows the strong force interactions between proton to proton, neutron to neutron, and proton to neutron. You can see here that the proton to neutron attraction is twice as strong as all the others. That's why when the protons and neutrons are in good balance, you have very good strong attraction. However, when there's too many neutrons, too many weak neutron to neutron attractions, or too little neutrons, and too many weak proton to proton attractions, it gets more unstable. And this could be visualized by this instability curve. In this graph, you can see that when there's too little neutrons, it undergoes what's called beta plus radiation. And when there's too many neutrons, it undergoes what is called beta minus radiation. And that we will discuss in the next chapter. So that's a basic introduction to radioactivity and why nuclei emit radiation. That's all we've got for today. So please check out the next video on the different forms of radiation. So I said that this nuclei emits radiation, but what kinds of radiation, and what is that radiation made of exactly? That's for next time. Thank you for watching, and have a good day.